All right, chapter 3 is all about acids and bases. I'm sure a lot of you were exposed to acids and bases in Gen Chem, but it may have been a while for others of you. So we're going to review it at a pretty basic level, and then we'll delve into it a little bit deeper. There are two main theories, and they were both developed the same year. They were both developed in 1923. Does anybody know what the two theories are? Show of hands. What do you think the first one is? Arrhenius. So Arrhenius is one where it talks about hydronium and hydroxide, right? What's another one that's more specific? What was that one? Bronsted Lowry was one. All right. Does anybody remember what Bronsted Lowry acid-base theory describes? Transfer of protons. So Bronsted Lowry really describes the movement of protons. So I'll describe protons as H+. Does anybody know the other theory? Lewis. So Lewis acid-base theory is really, really important. And instead of describing acids as a movement of protons, he describes it as movement of what? Electrons. Don't worry if you don't remember these, we'll review them in quite a bit of detail. Gilbert Lewis was that guy who I said was nominated for the Nobel Prize 23 times and never got the Nobel Prize. Again, this was one of his great contributions to organic chemistry that is essential to our understanding of acid-base theory. Let's start with the Bronsted-Lowry acid-base theory, and we'll describe it in a fair amount of detail. So the Bronsted-Lowry acid-base theory, we already said, describes the movement of protons. Specifically, acids donate or accept protons. Yeah, acids donate protons. They're the things giving that proton up. That means that bases must accept protons. Pretty simple concept. And we can show this using a pretty simplistic chemical equation where we've got a proton, and this is covalently bound to A. And then over here, I've got B with a lone pair. And we know that this can be in equilibrium. Actually, let me change this to a green B. I like color coding these. And the end result is, that A loses the proton, gains a lone pair and a negative charge, and then B is going to gain that proton, and it now has a positive charge. We typically, like I said, describe the thing that loses the proton as the acid. That means B is our base. Pretty convenient. What do we call A minus on the right-hand side if it lost its proton? Conjugate base, right? So in this case, it no longer has a proton to give up. It already gave it up. We call this the conjugate base. That means that B, since it has that proton now, is now our conjugate acid. What does the arrow in between represent? Equilibrium arrow. So oftentimes this transfer of protons isn't a one-way street. It can occur in both directions. It could be 50-50. It could be 99.999999% on one side and 0.000001% on the other side. But oftentimes we show this transfer using equilibrium arrows because technically you could show it going both ways. There are two important concepts that we need to remember anytime we're thinking about acids and bases. The first one is that strong acids form stable or unstable conjugate bases. What do you guys think? Stable. If we've got a strong acid, usually we're going to form a super duper stable conjugate base. So strong acids form stable or weak conjugate bases. I use the term stable and weak interchangeably during this acid-base section. That means that that conjugate base that we form doesn't really want to take that proton back. In fact, that acid's so happy giving up that proton, it doesn't ever want to take it back and push the equilibrium in the opposite direction. So that's how we can define a strong acid in very generic terms. The same is true for strong bases. Strong bases form stable or weak conjugate acids. So for example, if that B with the lone pair is super duper strong, we're going to form a conjugate acid that doesn't want to give up that proton. It would rather hang on to it. It's going to be nice and stable. In fact, it's going to be a really weak acid because it doesn't want to give that proton back. Does that make sense? A little abstract. We're talking about things with A's and B's. But let's define our equilibrium a little bit. I know some of you got this drilled into you, but let's practice. So the first thing we need to do is define this equilibrium, and like I said, we've got usually an acid in solution with water. That means we throw in some equilibrium arrows and we'd say, all right, if we've got an acid in water, we're going to form the hydronium ion, and then we're going to form our conjugate base, right? So let's come up with an equation for this, right? We've got KEQ, that's our equilibrium constant. What would our equilibrium equation be? Some of you guys remember this? It's concentration of products over reactants, right? The equilibrium. So what we're going to do is we'll say the equilibrium is going to be defined as the concentration of hydronium times our concentration of our conjugate base. Yeah, over the concentration of our starting materials, which was our acid and water. Right?
Don't we not include water because it's pure liquid?
That's what we're going to talk about here in a second. Yeah, you're getting ahead. All right, so we've got this really nice equilibrium constant. But you're right, water is a constant, right? So in this case, what we're going to do is we're going to pull this constant over to this side. So algebraically, we can say, all right, KEQ times this constant of water can be defined as this concentration of hydronium times our concentration of our conjugate base. And this is now over our concentration of our acid without water. So really, we just multiplied both sides by that concentration of water because it's a constant. Make sense? We can simplify this even further, and we can say that this whole expression can be defined as Ka. Because this is always what we use to look at acids in solution with water. This is Ka expression. So let's even box this in a red box just to indicate that this is super important. All right, so now the question is, if we've got a large Ka, what does that say about our acid? Yeah, if our Ka is large, that means our concentration of the hydronium ion is also large. Our concentration of our acid with the proton is quite low. So Ka let me reword this. Large Ka equals a strong acid. Small Ka equals a weak acid. Whoop. This can be a little ambiguous. How do we define strong and weak? That's up to some interpretation, right? What we'll do is we'll take a look at some examples, and then we'll try to come up with a term that's a little bit more clear. The first example I'll give you involves HCl. What's that name? Or how do we name HCl? Hydrochloric acid. A lot of you guys use this in your titration labs. You could say, all right, hydrochloric acid in water is going to form H3O plus and Cl minus. So chloride in this case will be our conjugate base. Hydronium will be our conjugate acid. If we think about the Ka for this reaction, it's going to be our concentration of Cl minus times our concentration of H3O plus over our concentration of HCl. If you calculate this, it's roughly 100 million. Does that mean HCl is a strong acid or weak acid? Strong. All right, second example. This time I'm going to use methane, so CH4 plus water. Again, this is in equilibrium. Could form H3O plus, and then what would our conjugate base be? Yeah, CH3 minus, right? So we're going to form CH3 minus. Let me move this negative charge over to the carbon. All right, same sort of thing. We'll calculate our Ka. We know that our Ka is going to be equal to our concentration of CH3 minus times our concentration of H3O plus over our concentration of CH4, our methane. Does anybody think this is going to be a large number or a small number?
Small.
Small. All right. If we do this, my hand might start cramping. It'll be 0.0000000000000. In fact, I don't want to write them all. Whoa. In fact, we have 48 zeros after the decimal. The probability of methane losing a proton is less than the probability of finding one atom in the universe. It's an incredibly small probability, to the extent where it's not even really going to ever happen. Oftentimes, to explain these super wacky ratios of our acid in solution to our conjugate acid and so on, we end up using a trick. Does anybody remember what that trick is to condense all those zeros?
Negative log.
Yeah, negative log, or our pKa scale, right? So if we do this, oftentimes to describe that 48 zeros, we just say, all right, this has a pKa of 48. Conversely, if we go up and we look at our hydrochloric acid example, how many zeros do we have? 8. However, because it's a negative log scale, this will be pKa of negative 8. So this pKa system really saves us that hassle of writing out a bazillion zeros, prevents your hand from cramping, and it's a nice way of describing that order of magnitude. So anytime you've got a pKa difference of 1, that means the one with the lower pKa is 10 times more acidic than the one with the higher pKa. It's a little confusing to think about, but let's really quickly define and review pKa. So pKa is equal to negative log of that Ka value. Sometimes students will ask me, does that P have anything to do with pH?
Yeah.
What do you guys think?
Yeah, it's the same.
Yeah, it's the same mathematical operator. P is always negative log of something. So in the case of pH, that's negative log of your proton concentration or your hydronium concentration in solution. So in this case, let's make a little note. A small pKa equals a strong acid. A large pKa equals a weak acid. Oftentimes the benchmark that I use is 15. 15 is the pKa of water. So if you've got a pKa of lower than 15, That means it's more acidic than water. We could consider it a relatively strong acid, right? It's going to drop your pH if you put it into solution. If you've got a pKa larger than 15, means it's a pretty weak acid. So much so, in fact, water would rather transfer its protons to it than anything else. So we can look at that. I don't expect my students to memorize pKa values because it can get super duper mind-bogglingly complicated. And why memorize something if you can look it up in a chart? So, let's do this.
Would the pKa of water be 14 though? Because it's 1 times 10 to the negative 14th is kW.
So I'll show you guys the table. It's not quite 14.
Because of temperature.
It can be dependent on temperature, though. So let's take a look on the website under useful links. You go down here. I've got some useful resources. pKa table right there. So if you click on that, this guy named Dave Evans at Harvard and his research group created a really nice table for us to use. There's some really simplified versions in your book. And you can see right here, oh, they're separating it out into functional groups. It's a good thing I remembered all my functional group names. If you go to the first alcohol, we've got HOH, also known as water. If you look at the pKa, it's listed as 15.7, so you don't have to memorize it necessarily. It's good to remember some benchmark values like water, for example. And then over here, you'll see another number in brackets. You'll notice up top on the table legend, we've got pKa value, and then it says H2O, and this one says DMSO. The first one without the brackets is the pKa value in water. Oftentimes, though, chemists can't get things to dissolve in water very well, so they test them in a solvent called dimethyl sulfoxide. It's abbreviated as DMSO, and those are the values in the brackets. So if you're in a situation where you can't find values in water, you may see this. You only want to compare the pKa values in DMSO to other pKa values in DMSO. And same thing with water. You don't want to compare something that's got a value in water to something that's got a value in DMSO. That's apples and oranges at that point. This is a really nice table. We'll use it quite a bit in this next chapter, but I think that's where we'll end off today. Also remember, if you have lab later this week, remember to bring your herbs in. We're going to distill those essential oils in lab.
Do azeotrope